There must be the deer flying up there. Yeah, the bugs got caught.
Mark,
Oh, you want to play?
it's time. Connections.
다시 한번 해볼게요.
Daddy?
Yo?
What?
What?
Daddy's one?
Let's put it right here.
Daddy Harlem?
Ain't no way the first one I can wrong.
I'm guessing this way
You
is.
want to double up?
All right. So let's have a look at this GM formula here. Right away, for BJTs, how did you find GM? What was it a function of? Just IC. Because VT, you normally do not control. You do not, put this device in a fridge or something to change VT. So VT is usually whatever the operating temperature of your device is. You do not play with that. The only way to control IC was by controlling, to control GM was by controlling IC. So if you wanted a higher GM, you had to consume more power at DC because that IC was DC power, right? For MOSFETs, well, this is a little bit of a good news. Actually, let me expand this. Let me write this as this other alternative formula. I'm going to multiply this thing. So remember, what was the ID formula? ID was 1/2 mu n Cox W/L times VGS minus VTH squared. Right? And look at this formula at the bottom. If I multiply the one at the top by 2 mu n Cox W/L, I have the bottom one squared, right? Or I can find Gn from this expression.
Like division plus, right? If and like commands like
Including operations.
Yeah, right.
And of course, this is DC ID, right? And then also, looking at the equation at the top and the equation at the bottom, you can see that you could also write this as 2ID over VGS minus VTH. Right? All three of them are the same. Depending on what is available to you, what information you have, you're going to use one of these to calculate your GM quickly. But point here is that for GM, to play with GM, you have one extra parameter in addition to your ID that you had before, IC for BJTs. You can also play with the dimension of the device. Same VGS minus VTH. If you want more current, if you want, a higher change conductance, you make your device wider. In integrated circuits, you can do that. That's it. Doubling the width is like putting 2 transistors in parallel. So you can do that as for a MOSFET. From the second formula, you see a little bit of bad news. Bad news is because for BJT, if you doubled IC, you doubled your GM. The gain was GMRC. So you doubled the gain. Over here, if you double ID, you only increase your GM by 40%. Right? Square root 2. If you want to have double the GM, you have to increase ID by a factor of 4. Right? So if you have a discrete device that you cannot play with its dimensions, you have to put a lot more current through it in order to get double the GM or triple the GM or things like that. So from this equation, you see why a BJT can be a better amplifier. Your GM, first of all, that exponential relationship right away means that it is more sensitive compared to the quadratic equation. Quadratic rate changes are more slow. Exponential, it's super sensitive to any change at dBE. Quadratic is slower by nature, but you see it here. With the BJT, you double ID, IC, collector current, you get twice the GM, twice the change conductance. For MOSFET, you get a little bit less. However, for MOSFET, you have that size. You can play with W2L and compensate for that to some extent. In a lot of cases, you go and design your circuit. When you're designing your circuit and you're shooting for some GM, you usually know what your ID is. So I can use the second formula to find my GM. But if you're analyzing a circuit, maybe the first one is easier, because when we are analyzing circuits, you usually find voltages and then currents. But voltages are usually the first things that we find. And if you happen to know what is happening around your device, let's say you're biasing with the current source and you just have the VGS minus VTH value, but this last one is the easiest one to use. Has no technology parameters in it. Okay? So let's use that model in the circuit, see what happens. So I want to find the gain of this circuit.
Makes for the cheap strategy. Probably should have made me
Yeah.
by playing her.
Okay?
Oh, this is stupid.
So I know the transistor parameters. I'm asked to find what is the out over Vn for this circuit. Okay? So what do I do?
Write the equation for us.
Assume an operating
Hmm?
region. Assume an operating region.
Assume an operating region. Okay, so let me make your life a little bit easier. It's not always true. We can actually reuse devices. We use MOSFETs in triode region and analog electronics a lot because they give you control over the value of a resistor. I like that. But usually when the device is shown in a circuit like this, it is most likely an active region. Right? And especially because I'm driving the gate with a small signal source. If the gate was connected to a big forceful voltage, then maybe I would be using this as a switch or control resistor. But in this case, it's most likely an active. But you know what you said is correct. We assume a region of operation. We solve the circuit, we verify the assumption. So solving the circuit, we do it at DC first. How do I solve this? I didn't put the next assignment online so that you guys go and do a little bit of practice with the suggested problems from the textbook. They're a little bit easier. But I'm going to post the assignment soon. Anyways, tell me, how do I solve this?
Well, we have an equation for ID.
We have an equation for ID. Good. So, right here by the assumption, I have this equation for ID. So looking at this equation, I know the constants, I don't know VGS, I don't know ID, obviously. So, two unknowns, I need one more equation. Where do I get the other equation?
KVL.
KVL where?
From top to bottom.
Yeah.
Bad idea.
Sorry.
You have to. We don't go across a current source with KVL. If this device is in active region, the drain is the current source, right? So you're going to introduce VDS into your equations. That's another unknown. It's not that you cannot write KVL, you can write KVL. But you
Not a constant.
have one more unknown. Right? So you have to come up with yet another equation. So what else can I do?
Multiple analysis. I'm just curious.
VGS and DRS.
So I can write a KVL from gate to the negative supply. Right? Going from gate to the negative supply. Then let's just do that and see what I get.
I think it's like a cross.
This is the path I take or intended. So KVL. So V gate, DC voltage at the gate is
top to
0.
bottom, but he's saying
So
from
0 is equal to
Oh, I didn't know you could do that.
VGS.
That's okay.
And then what is the current through RS? The voltage drop across RS, right? So what is the current through RS?
It's just
GS over R. It's not? GS over R is. No.
IDR.
ID, right? Because IS is the same as ID. It is IS, but ID and IS are equal. So, plus IDRS minus 1. I end up at the negative supply, minus 1. Okay? And good news, the same variables that I have here in this equation are the same as the ones in the top equation. 2 equations, 2 unknowns, I should be able to solve this. So you can solve for VGS or ID, right? So what you can do is that you can say, from here you can find ID, say ID is 1 minus VGS divided by RS, right? And plug it into that equation, you'll have one equation for ID that you can solve. Or you can find VGS from this equation and plug it into the equation in the above. And, you can write ID that is equal to VGS minus plus 1 minus divided by RS, put it on the left side, we have an equation for VGS. Or you can write VGS is equal to 1 minus IDRS, again plug it into this equation and solve that equation for ID. It's going to be a quadratic equation in either case, right? I'd like to solve it for VGS. That was the question.
Yeah, does ID always equal IS for any
Yes.
losses?
Any
region?
As long as you do not turn on the body. As long as your body voltage is low enough to keep those two diodes off, ID and IS are always equal.
Okay.
So that's a situation that should never happen, that you turn on one of those diodes. That should never happen. You keep the body voltage as low as possible to make sure that never happens.
And that's always the same for PMOSs as well?
PMOS and MOS, active, triode, cutoff, all. Okay, so I'm gonna find the ID from this equation and plug it in the above. Okay.
Yes, I said that.
Okay, and then solve this. solve this and work that there's no answers. So what do I get for VGS? Actually, I shouldn't have the numbers here. No, I have the numbers. So you get two values. So, well, that's the equation, you get two answers. Which one do I take?
The one that satisfies.
Hmm?
The one that satisfies the active region constraint?
The ones that puts it in active region, because that was my assumption. Active region is VGS is larger than the threshold. The threshold voltage is half a volt.
So that's we.
So the positive one is the one that I pick. It is supporting my assumption. It doesn't mean my assumption is correct. Right? So I'm following my assumption. I'm following the original thought I had. So, because the top one is supporting my assumption, I have an easy work from here. Now, you can solve for ID, right? You can solve for ID and you'll get two answers for ID. Sometimes it's not easy to see which one is supporting your answer, your assumption, because you may get two positive values for ID. Right? So you may get 100 micron or 200 micron. If the device is active, both of them can be correct. So you have to go and still figure out, which one is making VGS larger than that. Usually we get one positive and one negative value for ID. So it's easy to root out the one that is not correct. But for VGS, you see, you right away see it. Okay, so if that's the case, then this gives you an ID of how much? 86 microns. And then with this, you can go and check the device is active. Right? You check VGD, and you show it is less than the threshold voltage, and the device will be active. Right? Gate voltage is 0, 86 microns through 5K, it's 0.4 volts. And I have 0.6 volts for VGD. Minus 0.6. Right? So this is less than VGH. Okay, so this is my current. ID is 86 microns. But I'm not done yet. I'm essentially at the beginning of the work. I need to find V out, the change in the output voltage when a small signal input has applied to the device. So I go and draw my small signal circuit. I've done that a million times by now. Not a problem to draw the small signal circuit. Draw my transistor first, because that's usually the most complex device in a circuit. And I attach whatever that has to be attached to that wire. This is my transistor. Between source and the negative supply, I have the RS. Negative supply is a DC supply, so it becomes a ground connection. Between drain and positive supply, I have the RV, but positive supply again is a DC value, so it becomes ground. My V out was taken from the drain of the device, and the gate is connected to the. This is the small signal equivalent circuit. You've seen something more complicated than this before. All right, so guide me. What should I do?
Calculate GF.
Well, we need to find G. Good. Okay, so 86 microns. So I have that formula 2ID divided by VGS minus VTH, right? So I have VGS. So you get a value. It's 0.42 milliseconds. I need to find V out over V in. That was what the question wanted. So I start from in. I need to find V out. So what is V out in this circuit? IDRD, but it's small signal ID. So what is the small signal ID? GMVGS RD, right?
That's it.
Nice.
Not dumb.
That's the current times the resistance, right?
Is there a negative
Negative?
sign?
Negative. We're going up this resistor. Okay? Okay, so GMVGS RD. Okay, so I have V out, but I have VGS that I don't know. How do I find VGS? And I want to relate V out to V in eventually because I want to find V out over V in. So how do I get rid of VGS and find a relationship to V in? A connection between the two.
Is it
Yeah.
BG?
V out and V in.
So it's like same as what we did the pi models, right?
Is it D and equal
V and
VGS?
VGS, and then the current, or yeah, some currents in there.
What do I do?
KVL.
KVL back.
V into RS.
V into
RS.
Yeah.
Oh yeah, and the current to this
Yeah.
one is 0.
And then, but then it,
it's okay. You can go across the open circuit. You can write KVL back.
have the voltage drop. It's just yes.
It's just
Yeah.
0.
Plus, okay, so V in is this voltage plus this voltage. What is this voltage?
GMVS RS.
GMVGS times
Yeah.
RS. So same as IDRS, right? Same current, same as before. Plus GMVGS RS. Positive or negative? GMVGS RS. Positive or negative?
Positive.
positive.
Positive,
This
because
is
I'm
going
pushing
that
the current
direction.
down this resistance, right?
This is a vector.
Okay.
This time. What do you
Good,
think?
so I know V in, so this is not an unknown. I have one equation VGS, one unknown VGS here, and two unknowns VGS, two equations, two unknowns. I'm good. So what I do is that I find VGS from this equation, plug it in here, and done. So from here I can see that VGS is equal to V in divided by 1 plus GMRS. Okay? So plug that into the equation in above. Therefore, V out is equal to minus GMRV V in over 1 plus GMRS. Or if you want V out over V in, just divide them by each other. Right? Just V out over V. And here time. Does this look familiar?
Yes.
Yeah.
What does it look like?
Same
Pi
gain
mod.
as a common
Common emitter.
emitter.
Right? So say RC and RE, you are back to that stage, that same formula. Right? This is, you'll see it in the next lecture, this is called the common source stage.
Oh no.
Source and emitter are equivalent or similar, drain and collector are similar, gate and base are similar. So this is called the common source stage. The gate is exactly like a common emitter stage in terms of how it looks like. GMRD, if you want more gain, increase RD, increase GM. If you want more gain, get rid of RS, bypass it, do something about it, right? All those stuff that we talked about, a common emitter stage more or less apply.
When we make the equation for V in, why are we allowed to make a KVL over an open circuit? Is that like not allowed?
Why not?
Because you need a closed loop.
Why not?
Isn't that like a
No,
law or
well,
something?
okay.
No, but it's
No, I am in a closed loop.
See,
So I start from ground, go across this, go back to ground.
How do you jump over air?
What's air but? Why air?
It's just a
current, it's a voltage
Is that allowed?
Yeah, you close the loop, right? Because what does KVL says? KVL say that if you start from any node in the circuit and go back to that same node, all the voltages should add up to 0. And that's what KVL says. Okay, so I start from here. Minus V in plus VGS plus IDRS should be zero.
Easy just hung up on the because it's open circuit.
VN is just VGS, right? VN is just VGS, right?
Plus the RS current and stuff.
Oh,
Okay, so so that's that. So that's how we use the small signal model. Everything is easier than what it was for BJTs. Once you get to the small signal analysis, life is easier than what we saw before. There are some differences. We're going to talk about the differences between the stages that you make with MOSFETs and BJTs in the next lecture. But before we end the discussion on DC analysis and DC model, let's talk about the other guy,
AC.
the PMOS.
oh, the PMOS.
Oh, it's just the opposite. So it's P and P in the thing. Well, I said it louder.
Wow, what am I actually? Keep it up, no, you can't.
Structurally, exactly the same. You just make it on a substrate with the opposite polarity, and drain and source, instead of you dope them with N-type dopants, you dope them with P-type dopants, right? And then you can see that all those stories we said before apply here. The only difference is that I want to invert the doping at the surface from N-type to P-type. Okay? So what I need to do is that I need to attract holes to the surface. To attract holes to the surface, I need to apply negative voltage, because holes are positive charge gates, right? So I apply a negative charge, a negative gate voltage, make it large enough so that you have a lot of holes at the surface, and you create a channel between the P regions of drain and source. And the rest of the story is the same, equations are the same, everything is very
Basically
simple.
with positive.
The symbol for a PMOSFET is this.
Wow.
Again, the identify source, because in analog electronics it matters. The direction of the arrow points towards the channel, right?
Oh, that's good.
Channel, your channel is P-type in this case. This is the direction of your arrow. And IS goes in, ID comes out. IG is 0, like before. Okay? So therefore, ID and IS are equal. So I don't even bother writing IS. It is ID going in, ID coming out. Source, drain, feed. Okay? And then of course you still have that body channel or body connection. For the two diodes over here, so the two diodes, if you look at them inside this device, they look like this. You still want to keep them reverse biased. If you want to keep them reverse biased, you want to connect the N region, the substrate, the body of your device to the most positive voltage in your circuit.
I said that.
So if you're running the circuit from, let's say, 0 and 5, you connect the body of your PMOSFETs to the 5. Like before, a lot of discrete devices have the body and source terminals connected internally. Because usually the source terminal is at a higher voltage than drain. If they do that, it becomes asymmetric. But for integrated devices, we have the choice. You make sure that the body is connected to the most positive voltage in your circuit. Now, the main difference here is that the threshold is negative. Because in a NMOS, you wanted to bring electrons to the surface. You apply the positive voltage. Now you want to bring holes to the surface. You need to apply a negative voltage. To create that channel, you need a negative voltage, a minimum negative voltage. That is your threshold. But all those stories still apply. So for the operating regions of an PMOS, you have, again, 3 regions cut off, where I don't have a channel at either end. So what that is VGS and what is VGE? relative to VTH. So I know I'm comparing this to VTH.
No, much less.
Larger or smaller
Small.
than VTH? Or do I put here, larger or smaller?
Smaller.
VGS larger than VTH?
Oh.
VTH is negative. To have a channel, I want something more negative. Right?
Oh, so you're right. Why do you do that? I don't know. Is it figurating? Fix it.
Sorry.
Why do you do that?
Who said larger? I'm making, I'm confusing myself.
No, he's a figure game.
You're right.
Yes.
I don't want to have a channel. So it's a negative voltage. I want to be above that negative voltage. If it is -1, I want to be at, let's say, 0, at 1, at -0.5. Right? So for cutoff,
Threshold is like the minimum.
for NMOS, this meant I had a channel because the threshold voltage was positive. For an PMOS, this means you don't have a channel. Same thing for triode and same thing for so for triode, you have a channel at both ends. So the gate source voltage must be smaller than your threshold voltage, and the gate drain voltage must also be smaller than your threshold voltage, right? And for saturation or active,
Yeah, just as Lucius wants.
VGS is less than the threshold voltage, more negative. Instead of -1, I have -2, right? But I don't have a channel as the drain, then VGE is larger than VTH. Equations are the same again. So here ID is 0 and IG is always 0. And because ID is 0, IS is also 0. For saturation, your ID is, here's a slight difference, 1/2 mu P instead of mu N. Mu N is the mobility of electrons, mu P is the mobility of holes. They are different, they're a little bit different. Of course, depending on the semiconductor you use, they have a different number, but for silicon, it turns out that electrons move faster than holes. Okay? So for that reason, N MOSFETs are faster than P MOSFETs. If you have the choice in analog electronics, for example, to choose one of them for your core amplifier, you use an NMOS because it is faster. Same technology, it is faster. I like to write it this way. And then the equation for triode is similar as well, right? Same thing, okay, I'm going to focus on something that I find confusing in some textbooks. Okay, so if VTH is a negative value, let's say -1, right? And VGS is smaller than that, the absolute value of VGS is larger. So it's -2. So if you compare the absolute values, it's larger. So some books would like to write this as absolute value of VGS is larger than absolute value of VTH.
That makes sense.
And the reason they do that then is that this becomes similar to what you have for an NMOS.
Yeah.
Right? I don't like that because I think that absolute value can create some unnecessary uncertainty. Just keep in mind, VTH is negative, VGD has to be less negative or more negative depending on whether you want to have a channel at that end or not. And same thing for VGD. And then this equation, when you write it here, for an NMOS, you have a VGS that is larger than VTH. So this VGS minus VTH will become a positive number. So it's a 2 volts minus 1, so that's 1. For a PMOS, VGS is more negative than VTH. So it is, let's say, -2 minus -1. So it becomes -1. It's a negative number. But squared, who cares?
Does that mean that current is going the other way then?
No,
No?
no, it's square. You
Oh,
square.
square, sorry, yeah.
You square. Okay? But the direction of the current is
Yeah.
out of drain. Right? So I don't like that absolute value thing that much. If it helps you, makes it similar to NMOS and helps you use it, I don't like it. I think, once you start writing equations, you don't want to have an absolute value in it, because that means two values. I don't like that. As long as you can keep track of what's happening in your circuit, you don't need to do that. So we have only a minute left. Here's an example for PMOS. Have a look at it yourself.
It's the same thing. It's the same thing.
Easy enough. And I just want to mention one thing before we close this chapter. Chapter 5 is, no, not chapter 5.
The second, third quiz is second. It's not gonna
Scale, scale, scale.
Here we go. How much on scale? Yeah.
So as you noticed, we make PMOS and NMOS devices on different substrates. An NMOS is made on a P substrate, a PMOS is made on an N substrate, right? So what that means is that you cannot make them side by side on the same substrate, because your wafer, whatever you produce, is either N-type or P-type. Right? So when you hear about CMOS technology, in CMOS technology, they make both of these devices on the same substrate, NMOSes and PMOSes. But what they do is that they take one type of the substrate, either P-type or N-type, and create regions that are of the opposite polarity. Right? So there's a little bit of, they call it a valve. They create a valve that is N-type, and they make P-types inside that valve. Now the body contact for these P-type devices is the voltage of that valve. And the body contact for the NMOS device here is your substrate voltage. Right? So this is how you make N-type and P-type devices next to each other. Extremely important for digital stuff, because transistors are the smallest things you can make. And digital electronics need a lot of transistors. So if you want to have gates and everything else, you need both P-type devices and N-type devices. And you need to find a way to make them side by side. You can do the job of, let's say, PMOS with a resistor, and then still make your gate. You make gates with diodes and resistors. You can make a gate with a resistor and a transistor, a BJT. You can do the same thing with a MOSFET, but your device, your circuit will be large. To make your circuit compact, to put as many gates, memory elements, all those digital stuff as you can on a small area, you want to have both devices made in the same technology. So very important, this is the backbone of this entire microelectronic industry, why NVIDIA is going up and why IBM is sucking down and all that. This technology, some of you are going to be better than the rest. Right? How to make them side by side. Modern technologies actually, they put both of them in their own valves. So they take some substrate, create a valve for NMOS devices, create a valve for PMOS devices. And then you make the devices the way you want. Integrated circuits, look at this PMOS. I have control over the body voltage now. It's not automatically connected to the lowest voltage in your circuit. I can connect it to the source of my device, I can connect it to some other voltage. You can do that. If you want, you can play with the body voltage. The first thing that it affects is the threshold voltage of this guy. Sometimes you do that. You want temperature compensation, some other compensation. You play with the body voltage, but usually you don't mess with it.
Well, would that also mean that everywhere that you have your P substrate is all the same voltage?
Yeah.
Is that ever a problem?
Good question. So the question is that, if I'm showing you two transistors here, but what if I have another NMOS right here? And then another NMOS like after that, and things like that, right? So for MOSFETs, it's not a big deal. But you need to isolate these devices from each other electrically. So for MOSFETs, that's not a big deal because the current is going to stay between these two terminals. If the device next to it is a little bit further away, that's not a big deal. For BJTs, it was a bit of a problem because a lot of BJTs may have a common collector or a common emitter terminal. So you need trench isolation. Okay, I gave that. you use two different ways. You either remove a little bit of substrate here, that's called trench isolation, but that's tricky because that trench will have dimensions, it will add to the size of the check. So what they used to do is that they had narrow trenches and fill it up with some dielectric or something. Right? That's one of the possibilities. Or you can, let's say, I'm sorry. Or you can see
Sign. Go home.
so something like this, assume that I stretch it to this, right? All the way to the bottom. And what I can do is that it's a diagram, P, or let's say N type. I can stretch it all the way to the bottom. I have a diode, I can reverse bias that diode. And using reverse bias diodes, I can separate different regions of the circuit from each other. So that's called junction isolation. So there are two different ways of doing it, trench isolation or junction isolation. But with MOSFETs, usually you can have this device in its own well, the next device is in its own well. Right? So if I make a different device here in its own well, the currents are not, they don't affect each other. Because this guy is reverse bias. I have a big reverse bias junction.